Hi, I'm Goh Zee Xin. I will do the video presentation of this project. This project is purpose to view the effect of panel length towards the FinFET. So at here, I will using the nanohub.org tools to simulate it. So this one is the nanohub.org app. And first, I will choose the device type as FinFET, and dimension is 2D. Metal type is metal, which remain the default. Then I will go to the structure. And here, the channel Y is equal to 30 nanometer, and T-ops is equal to 2.5 nanometer. And we go to geometry Y. At here, I will using the get length equal to 60 nanometer, and LS and LD is equal to 50 nanometer. And the gap overlap is remain the same 2 nanometer. And this one is geometry Z. And then topping source and drain topping concentration is 1 multiplied with 10 power of 19. And for the channel topping concentration, I will using 1 multiplied with 10 power of 15. And then the source topping type and drain topping type and channel topping type and poly topping type are remain the default. And for the Gaussian topping, I will enable it. And remaining is remain the default. Next, I will go to material. In general, this one dielectric is default. Other is also inside the default. For the gate contact watt function, I am using 4.60 watt. Other remain the default. This one is also remain the default. Temperature, I am using 300K. This one is also the default. So I will simulate it and get the IDVG characteristic. So inside the IDVG characteristic, we can see that when VD equal to 0.05 watt, which is the blue color graph, VTH is equal to 0.3. And when VD equal to 1 watt, which is the red color graph, the VTH is around 0.28 watt. And at here, both of the subthreshold slope for VD equal to 0.05 watt and VD equal to 1 watt is 80 milliwatt per decade. So when VD equal to 0.05 watt, the I off will equal to 3.22 multiplied with 10 power of negative 11. And when VD equal to 1 watt, the I off will equal to 1.02 multiplied with 10 power of negative 10. Then for the ion, when VD equal to 1 watt, the ion will equal to 0.00041 watt. And when VD equal to 0.05, the ion will equal to 9.3 multiplied with 10 power of negative 5. So at here, we can get the DIBL equal to 31.1 milliwatt over watt. And then next, I will go to simulate the 45 μm gate length. So at here, I will change at the structure geometry Y. So 45 nanometer. Other will be remain the same. So for now, I will get the new IV characteristic. So this one is the IV characteristic for gate length equal to 45 nm. So at here we can see that the VTH for VD equal to 0.05 watt is around 0.27. And when VD equal to 1, the VTH is around 0.23 watt. So at here the subthreshold slot is increased to around 100 milliwatt over decade. And when VD equal to 0.05 watt, the I off is equal to 1.31 multiplied with 10 power of negative 10. And for VD equal to 1 watt, the I off is equal to 9.44 multiplied with 10 power of negative 10. For the ion, when VD equal to 1 watt, E is equal to 0.00041. And when VD equal to 0.05, the ID is equal to 9.67 multiplied with 10 power of negative 5 watt. So at here, the DLBL will increase to around 42.11 milliwatt per watt. And then I will go to simulate the gate length of 30 nanometer. Go to structure, geometry Y, and change here. Other will be the same. Simulate. So I will choose the IDVG. So this one is the IDVG curve when gate length is equal to 30 nanometer. So when gate length equal to 30 nanometer, the VD equal to 0.05 watt, the VTH is around 0.25 watt. And when VD equal to 1 watt, the VTH will be equal to around 0.13 watt. For the I off, when VD equal to 0.05 watt, is around 1.46 multiplied with 10 power of negative 9. And when VD equal to 1 watt, the I off will be around 4.36 multiplied with 10 power of negative 8. For the ion, when VD equal to 1, is around 0.00042. And when VD equal to 0.05, is around 0.001. So at here, the subthreshold also increase. It is more obvious when VD equal to 1 watt, the subthreshold slope is increased to around 120 milliwatt per decade. And the DIBL also increased to around 126.32 milliwatt per watt. So from the result obtained, it can be seen that the result is same as the theoretical. In the analysis conducted across varying channel length and drain voltage, we can observe the threshold voltage decrease consistently when the channel length is reduced. So this trend is evident at both low drain voltage when VD equal to 0.05 watt and also high drain voltage when VD equal to 1 watt. So this indicates the short channel length effect. The VDH degradation is more pronounced when higher drain voltage, which is the VD equal to 1 watt. So when the shortest channel length of 30 nanometer, the VDH at VD equal to 1 watt is significantly larger drop than VD equal to 0.05 watt. So this one is the difference reflect trend-induced barrier lowering DIBL, which is one of the critical short channel effect. So DIBL is defined as the reduction in threshold voltage due to increase in drain voltage. So when the channel length becomes shorter, the differential region of the source and drain will become merged, and the drain potential will penetrate more deeply into the channel. This penetration will lower the energy barrier between the source and channel, allowing carrier to be injected into the channel even when the gate voltage is below the nominal threshold. This means that the drain is assisting the gate in turning the device on, which should not be happen in a well-controlled long-channel device. So from the result obtained, we can see that the DIBL was observed to increase significantly when the channel length reduced. So the DIBL induced shift will cause the VDH to move in the negative direction, which is to the leftward on the IDVG curve toward the depletion region. So as a result, the I-off will increase, degrading the I-on over I-off ratio. So in DIBL, we can see also the subthreshold increase when the channel length reduce. So a higher subthreshold slope indicate the gate voltage must increase more to achieve the same decade rise in drain current, meaning the gate control become bigger in the short channel device. So in the device 3, which is length equal to 30 nanometer, we can see all of this behavior, which is high DIBL, increased subthreshold slope, and noticeable VTH roll off, which indicate the short channel length effect. To address short channel challenge, we will use the SOI technology. The SOI technology will show here. So this one is the SOI technology. The SOI technology is incorporate a thin layer of silicon separated from the substrate by a rear oxide box layer. This substrate effectively isolates the channel from the bulk substrate, minimizing the drain to channel coupling and separate the DIBL. Moreover, the SOI also reduce the junction capacitance, leakage current, and improve the gate's electrostatic control over the channel. So that's all for my video presentation, and thank you.